Hello everyone, welcome to the demo of extra credit project for ECE 417. This is Xinyang.
And this is Zicheng.
Okay, first I'll introduce the overview of our project. We have simulated an autonomous two-wheel robot in Weebots that uses lidar sensors, rule-based logic, and also the PID control to navigate and avoid obstacles in real time. As you can see on the right of the screen, this is our screenshot of the robots in the Weebot software. Okay, we use Weebots as our simulation platform. The robot consists of a yellow cylindrical body right here, two disc-shaped wheels for differential drive, and three lidar sensors, one facing forward right here, and two angled to the left and right. We also added two support spheres at the base, like the bottom of the cylindrical body, to stabilize the robot and prevent tilting during turns. Because the mechanical design of the robot, it might fall forward and backward uh, if we don't have this support. In terms of the robotics kinematics, the motion and sensor positioning are governed by transformation matrix. We utilize rotational matrix R and translational vector to get the homogeneous transformation matrix T. Um, as you can see, we use the XYZ as omega in the formula right here and plug in the angle as theta. We get the rotation matrix R, and we add the translation matrix vector 3 to get the T matrix right here. This positioning matrix ensures the correct orientation of the left wheel, and the calculation for the right wheel is similar. For the sensor part, the control logic is fully reactive. By default, the robot moves forward. If the forward lidar detects an obstacle within a certain range, it will compare the left and right lidar values and turns toward the side that has more clearance. Once the front is clear again, it resumes forward movement. Well, this approach mimics basic biological reflexes and also it ensures the adaptive real-time response.
We also add a PID controller to enhance the robot's stability and directional accuracy during forward motion. The controller input is the arrow, which is computed as the difference between left and the right lidar distance. This arrow reflects deviation from the center of the path. The PID controller calculates a correction to adjust the wheel speeds, keeping the robot centered. The whole controller contains three parts: proportional part, integral part, and derivative part, as shown at the right bottom. The arrow will feed into the PID. After processing the arrow and feed forward to the robots, the measured robot pulse is compared against the desired state, and the difference is fed back into the controller again. The controller makes the system dynamic and self-correcting. It will also reduce drift when moving forward, smoothen the trajectory, and ensure finer alignment in a narrow path. Here's the code we have for the PID. After we calculate the time and arrow, we will feed both input to the PID controller function. The correction will be the value that adjusts the left and right wheel to steer the robot toward the center. The right part of the code is triggered after an obstacle is detected, and the robot will turn into place until all other directions are clear. Two parts of the code works together to ensure the robot did not collide with any obstacles. And here is a short demo of our robots. As you can see, it will avoid all the obstacles it is facing. Yeah, also noticing that sometimes the robot is jerking. That's because the PID controller is overcorrecting or reacting too aggressive to arrows. We could probably limit the motor speed to prevent dramatic turns and avoid overreacting of the controller. And in the future, we plan to enhance our robot's autonomy by enabling it to build a map of the environment as it explores. This will allow the robot not only to avoid obstacles, but also understand and navigate its surroundings more intelligently. To achieve this, we aim to integrate additional sensors including GPS, compass, and pre-existing LiDAR. Using these inputs, the robot will implement a form of SLAM, simultaneously localizing and mapping. It will allow the robot to construct a 2D map of the world in the real time, track its own position within the map, and eventually plan paths to goal locations. This shift would make our robot more versatile in a complex and dynamic environments. In this project, we design and implement a mobile robot in Weebles that can autonomously navigate and avoid obstacles using a combination of LiDAR sensors and motor control. The robot uses a differential drive system, allowing it to move and turn freely, and is equipped with three LiDAR sensors to detect obstacles in the front and on both sides. Our control strategy is based on a reactive approach, where the robot continuously monitors its surroundings and adjusts its behavior in the real time. To improve stability and accuracy, we incorporate a PID controller that dynamically corrects the robot's direction based on the difference between left and right distance. Overall, our project is successful as the robot can safely and smoothly navigate through complex environments without a pre-built map. We demonstrate key concepts from ECE 470, including SE3 transformation, PID controller, and feedback loops. This is a successful project overall.
Okay,
Thank you.
thank you.